Hi, I'm Henry.
And I'm Arnav, and we're going to be discussing umbrella sampling, which is just a way to determine the free energy landscape of different chemical systems, especially when there is like an energy barrier in our system. So first, we're going to give some context and talk about potential energies, potential functions. These are just functions that define our energy of our system based on the positions only of different atoms or particles in our system. And these potential functions kind of implicitly define probability distributions of where we expect to observe the atoms or particles. So we're going to have a higher probability observing particles at low energy states, low potentials, and vice versa, and a low probability of observing particles at higher energy states. So let's talk about Monte Carlo simulation. Essentially, we want to be able to sample from the space of all configurations of all atoms and particles in our system. But this is a super high dimensional problem, right? We have to think about the positions of every single atom or particle. There's n particles, and there's kind of 3 dimensions each particle can operate in, right? Can move in. So this is kind of an n times 3 dimensional problem, which is super high dimensional. And to sample from this high dimensional probability distribution, we can't do it directly. We need to use Markov chain Monte Carlo. How does this work? We start with some initial molecular configuration, some initial positions of all the atoms in our system, and we propose a new configuration with a small sort of perturbation. And we accept this new configuration with some acceptance probability that depends on the energy difference of our final state, our proposed state, and our initial state. So if this energy difference is high, we have a low probability of accepting it, and vice versa. And then we kind of repeat and collect a bunch of samples. And we note that the distribution of the samples, as the number of samples gets very large, will tend towards the true probability distribution of our system. What are the challenges of sampling just using this standard method? Well, say we have energy barriers in our system. So let's look at this diagram on the right. We have 2 kind of potential wells. We have a low energy state at state A and a low energy state at state B. So if we start our sample, if we start our initial configuration kind of in the area, in the realm of our well on the left, our samples will get trapped in this local optima. It'll be very difficult to overcome this energy barrier, because say we make a small perturbation to our state, well, we're going to have a huge increase in energy. And the chance we accept that new configuration is going to be very low. So this is going to end up kind of resulting in us only getting samples from one sort of part of this probability distribution. So if we get trapped in local optima, we're going to have a lack of exploration of the entire distribution, and it's going to be very difficult to sample kind of rare events or high energy events. So what can we do to kind of remedy this? Well, we introduce additional potential functions to bias our sampling in one specific region of our probability distribution. And this is going to really encourage the exploration of new states. So we kind of overlay, we can see these blue dashed curves are our new bias functions that we're overlaying on top of our actual potential function. What this is going to do is kind of constrain our exploration to a small area of this potential energy domain, and we're going to really explore that state.
Umbrella sampling is a methodic way of using these biased potentials to run many simulations. So as you can see here, we might actually have hundreds of different bias potentials that we use on top of our energy landscape. Each of these simulations is going to produce a biased histogram of observed states. So for example, we might have this one bias, and if we look at as the bias moves across our energy landscape, the histogram of observed coordinates is going to be tightly coupled with the specific bias function. When we combine the histograms of all of these biased simulations, we notice that the combined histogram is actually quite flat. And therefore, while umbrella sampling does allow us to sample from all of these states, we need statistical methods to actually remove the bias that we've introduced. Importantly, we'll also note that the intervals must actually overlap, as otherwise we would get discontinuities. So first I'll talk quickly about what it means to actually unbias these biased probabilities. So as I said before, the histograms are biased probabilities coming from each simulation. This equation is what we use to unbias the probabilities. The variables A, K are the free energy due to each restraining potential K. And A naught is an arbitrary parameter that comes from the fact that we can never know the absolute free energy, only the relative free energies. This W is our bias potential K. And the bias probability window, the bias probability that we've generated from our kth simulation is this P tilde. Q here is the coordinate that we're actually applying this function over. So in the example before, this was just the x coordinate. And the goal here is to produce this unbiased potential P. We do this through two weights. The first weight corrects for the global free energy shift introduced by the bias potential. And so this essentially puts all of the different simulations on an equal playing field. And then this allows us to add more weight to states that we observed yet we biased against. So if we observe a state that's that we really had a bias function that had a high potential, yet we still see something crossing over that high added bias potential, then it's a pretty significant observation because it means that our underlying energy landscape is so significantly beneficial to be in that state that even with the bias, it still was observed. To iteratively solve this in a more methodical way, we use the weighted histogram analysis method, which is an iterative method that combines our biased window potentials into one global unbiased potential. We can derive the equations by minimizing the statistical error of the global potential, but for the sake of the time, we won't be doing that in this presentation. But the setup is essentially this. We want this global potential P of Q, and it comes from a weighting, so we have coefficients CK, a weighting of each unbiased potential from the prior slide. And we're essentially doing a form of constrained optimization because we want all of the coefficients to add up to 1.
All right, so now we wanted to actually apply this methodology to different systems. So we started with the simplest system, which is one particle moving in one dimension, and we have a 2-weld potential. So here we can see that we have our potential on the right. We have a well at x equals 0.5 and a well at x equals 1.5, and we have this large energy barrier at x equals 1. So you can see there's a large energy barrier, and we ran these simulations at low temperatures, T equals specifically temperature at 50 Kelvin. So this will make it difficult for traditional MCMC methods to kind of overcome this energy barrier and explore all the states because of the lack of kinetic energy in our system. So here are some preliminary results as we reconstruct the probability distribution that comes from our 2-weld potential. So on the left, we can see the red curve are our true, what we should observe, our true probability distribution that will come from that 2-weld potential. And the blue curve we can see is as we update the weights from our weighted histogram analysis method, this is as iterations increase of this method, we can see that our blue curve is kind of approaching the true probability distribution. And similarly on the right, this shows the energy landscape. So this is showing the blue curve as we again update the weights, kind of approaching the true energy landscape of this 2-weld system. So now we wanted to compare our umbrella sampling method with just our traditional MCMC methods. Here on the left, we can see the density of samples, or our probability distribution that we observe when we apply just normal Metropolis Hastings. And we can see our true distribution, as shown by the orange dashed curve, has 2 peaks, right, with our 2 different wells. But what we actually sample, we only see one kind of big peak at x equals 0.5. And that's essentially meaning that we're getting stuck in that well of x equals 0.5. So we probably initialized somewhere on this state in that well, and we're getting stuck because of the low temperature. We're not able to cross that energy barrier. And similarly, we can see on the right that because we're not able to cross that energy barrier, we're not able to reconstruct the full energy landscape of our system. We're only able to reconstruct the energy landscape in that one well. And now we just wanted to apply this to more complex 1D potential functions, so specifically a multi-well potential. And we can see that the same approach, the umbrella sampling approach, works for these more complex functions as we update the weights and learn the true energy landscape of our system. So in the future, we hope to extend to a two-dimensional potential energy surface. So we want to kind of increase the dimensions of our problem a little bit. And specifically, we want to apply to the Mueller-Brown potential landscape, which is a common potential energy landscape with multiple sort of energy wells in 2 dimensions. And so first, we want to increase the dimensions. And next, we hope to increase the number of particles in our system. So to make it, again, the system a little bit more complex and extend to a liquid argon system with again, multiple particles. Thank you for listening to our presentation, and yeah.